as we begin our study of how to do Hess law problems, which are adding chemical reactions together, it's important to remember three important truths about enthalpy. The first was that enthalpy was extrinsic, that the amount mattered, and that if I have a reaction that produces 80 kilojoules of energy, if I double the amount, I'm going to now produce 160. Second was that reversing the reaction would change the sign, but not the number. So if I take that same reaction that is producing 80 kilojoules of energy, if I reverse it, it's now going to consume 80 kilojoules of energy. The amount stays the same, but the sign will change from positive to negative, or negative to positive. The last thing was that enthalpy depends on the state of the reactants and products. So we have to watch whether or not a chemical is in the liquid, solid, gas, or even aqueous phase. So the first problem on your sheet looks like this. I've added some color coding to keep things kind of clear, but we have a target reaction, PCl5 reacting to form PCl3 plus Cl2. Right? We need to find what's the enthalpy change for our target reaction. We're given two reactions, the first one in black, P4 plus 6Cl2 react to form 4PCl3, and told its enthalpy, negative 2,439 kilojoules, so this means it's an exothermic reaction, and another reaction, 4PCl5 reacting to form P4 solid plus 10 chlorine gas, its delta H is 3,438 kilojoules, so it's endothermic. Because we can add these reactions together, and because it doesn't matter how you get to the target reaction, since enthalpy is also a state function, we can bring these two, the black and the orange equation, together to make our target equation. One of the things that I've done is I've lined up the arrows. This helps because the first thing we need to do is to make sure that things are on the proper side. So I'm looking for a match between my target and my given equations. So for example, PCl5 is on the reactant side. Down here, it's also on the reactant side. That's good. If it wasn't, I would have to flip this reaction over. PCl3 is on the product side, and here's PCl3 on the product side. And our last one, chlorine gas, is a product. It's a product on this equation too. And I'm not concerned that it's also showing up on the reactant side, because the next thing that we're going to look for is going to take care of that. So first, I check to see are things on the proper side of the arrow. If not, I'm going to flip them. I don't have to flip any of these. What about these things that aren't in our target reaction? P4 solid. This solid phosphorus is not on our reaction, so it has to disappear. So I want to see that there is some of it on both sides of the arrow. P4 over here, and P4 over here. Right. There's also the same number on each side of the arrow. So that tells me they're going to cancel out. The 6 chlorine over here are also going to be able to cancel out. But right now, everything seems to be lined up right. Things I don't want are on both sides of the arrow. Things I do want are on the proper side of the arrow. So I can just add these all together. And when I do that, I get this big long equation. And I can now just go through with a little algebra and say, if I treat the arrow like an equal sign, that P4 on both sides disappears, and that these 6 chlorine over here disappear, and they take 6 chlorine over here with them. That leaves me 4 chlorine on this side. So to neaten things up, I've added these two, the black and the orange equation, together. I can also add their enthalpies together. So if I get rid of the things I crossed out, I end up with 4 PCl5 making 4 PCl3 plus 4 chlorine gas. The enthalpy for that reaction is 999 kilojoules. Now that is not my target equation. My target equation does not have any coefficients. So to get rid of the coefficients, there's all these 4s. I would just divide everything by 4, including the enthalpy. So when I divide the enthalpy by 4, I get 249.8 kilojoules. That is the enthalpy of my target reaction.